Hi, welcome back to our third video for 3.1, the nature of exponential growth. In this video, we're going to do an example of exponential growth, an example that commonly comes up in real life scenarios. And as we go through this chapter, you'll continue to see more applications of exponential growth. So in this example, we're going to take a look at bacteria. So it says a type of bacteria grows so that it triples in number every day. On the day that Roger begins observing the bacteria, a sample has a population of 100. So we're first asked to find the population after each of the first 4 days. Then write an equation to model this growth. Then graph the relation and see if it is a function. And then determine how much bacteria will be there in 1 week. We're also going to add 2 weeks to that as well. We're going to look after 1 week and then 2 weeks. And then describe the pattern of finite differences for this relationship. So calculate the population for the first 4 days. So we start with 100. Okay? And then on day 1, it would triple. So we would take that 100 and we'd multiply it by 3, giving us 300. And each consecutive day, it's going to continue tripling. So day 2, we would take that 300 and multiply it by 3 again and get 900. And then we would take that 900 and multiply it by 3 again to get 2,700. So we can see it's always tripling each day. On day 4, 2,700 times 3 is 8,100. So we can see that bacteria is growing very quickly. Okay, so after 4 days, there would be 8,100 bacteria present. So we now want to find an equation to model this growth. Okay, an easy way to do this is to actually look at that data table in a little bit of a different way. So I said here, to better illustrate the relationship between the day and the population, express each population calculation in terms of the number of times the initial population is tripled. So what we mean by that is after day 1, it's been multiplied by 3 just once. So we write it as 3 to the exponent 1. That gives us 300. On day 2, that 100 would actually triple twice. It would triple once for day 1, and then it would triple a second time for day 2. So 3 squared gives us 9, so we would get that value of 900. If we're going to be multiplying by 3 again to get the next term, we would have 100 times 3 to the exponent 3, giving us 2,700. You guys get the idea. On day 4, we'd have 100 times 3 to the exponent 4. This is because we would have had to multiply by 3 4 times. So we write that power as 3 to the exponent 4. So what about n days? What if we let that bacteria sit for n days? Then we would have had to take in 100 and multiply it by 3 n times. So that could be written as 3 to the exponent n. So this actually helps us determine the equation. So we could say the equation relating to population p to the number of days n is p of n equal to 100 times 3 to the exponent n. We can see this is now an exponential relationship because our variable is now in the exponent. That's what's going to make this unit different than all the other ones. Our variable is now going to be the exponent. Okay, next we're asked to graph the relation. Is it a function? Explain. So if we plot those values, we would get something that looks like this. I sent a link for Desmos for this as well if you want to bring it up. So plotting the points individually and then testing our equation. Okay, y equals 300 times 3 to the x. We notice that that curve passes nicely through all those ordered pairs. Okay, is this a function? Well, it most certainly is. If we were to draw a vertical line test, we could see that it always passes through the green curve just once. So each x value has only one y value. So yes, it is a function. Okay, so it passes the vertical line test, and each n has only one value for p. Okay, you can't put a time frame in, or you can't put in a number of days and get two different values for the population. It doesn't work like that. So predict the population after 1 and 2 weeks. Well, if you notice in the previous slide how the data and the graph goes very quickly, which makes it hard to extrapolate information. So extrapolation just means when we're looking for information that's outside of our data point. So we were only given points up until the first 4 days, and we want to know what happens after 1 week. So that graph grows really quickly, and trying to graph it and get the y value is really difficult. So it's easier to work with the equation. So for 1 week, what we can do is we can use that equation that we found previously. And for the number of days, n, we should use the value 7. So if we substitute n equal to 7, which is 1 week, we could then calculate the population. So 3 to the 7 is 2,187. Multiply that by 100. We get 218,700 population. So that's the amount of bacteria after 1 week. Let's see what happens for the second week. So we would then substitute n equals 14 into the equation, because now it's been 14 days. 3 to the 14, we can see it's a much bigger number, 4,782,969. Multiply that by 100, and then we get something over 478 million. So that would be the amount of bacteria after 2 weeks. That should say after 2 weeks. So we can see how this grows really, really quickly. And even trying to graph this can actually be pretty difficult, because you're only going to get a few points, okay, before the numbers start getting like too big. All right, lastly, I want to describe the pattern of the finite differences for this relationship. So there's our data, and here's our first set of differences. So 300 minus 100 gives us 200. You guys get the idea. And then comparing these finite differences, we can then try to determine the second differences and see what happens. So 600 minus 200. So what I notice for the second differences as well is that they're not constant. Our first differences aren't constant. The second differences aren't constant. But I also notice a ratio between successive terms and the first and second differences. And I notice there's a ratio of 3, meaning I can take one of them and multiply by 3 to get the next. Because that constant ratio exists, that means this will never reach a constant finite difference, which also means this must be an exponential function. So exponential functions continue to grow at increasing rates. So that's why they will always have that constant ratio in the first, second, and third, and so on differences. So that ratio will be present in all of them. So whenever you see a constant ratio like this, it doesn't matter if it's 3 or 2 or 1.5. Sometimes it may even be a half when we look at other examples. So as long as it's not 1, then it means the function has exponential growth. So what are exponential growth characteristics? So we've been talking about finite differences and the graphs. We were looking at patterns. So what we can summarize is that the pattern of growth for exponential functions is one that each term is multiplied by a constant amount to produce the next. Okay, so they'll always display a pattern of growth in which each term is multiplied by a constant amount, something greater than 1, to produce the next term. That's the only way it can grow, is if that value is greater than 1. So we've seen examples where we had stuff doubling. We went from 1 to 2 to 4 to 8 to 16. Notice we're always multiplying by 2 to get the next term. Okay. And the previous example, it was 3 because it was tripling. So exponential growth functions will always have that characteristic. Okay. Another one is that it produces a graph that increases at a constantly increasing rate. So that means the rate that it's growing at is also increasing. Okay. It's not like a linear function where it always goes up by 2 each time. So the rate that it's growing is also growing. That's how exponential functions work. That's what makes them grow so quickly. Okay, and the finite difference is you're going to notice a repeating pattern. So you'll see that there's a common ratio between successive terms. So the ratio of successive finite differences will be constant. Okay, and this is our last short example for this section. In this example, we're going to look at what it means to have 0 for an exponent. So throughout this chapter, we're going to talk about different exponents. We're going to talk about fraction exponents, 0 exponent, and even negative exponents. But for right now, we want to talk about what does it mean to have 0 for an exponent. So we're asked here to use the data in example 1 to determine the meaning of 3 to the exponent 0. So we're talking about the bacteria that Roger was studying. So this population of bacteria. So if you notice there's a pattern here, 3 to the 4, 3 to the 3, 3 to the 2, 3 to the 1. Well, that means if I follow that pattern and extend it, this should actually be 100 times 3 to the exponent 0. So extending that pattern, right, we would get this. So this tells me that 3 to the 0 is not 0. So on day 0, I've multiplied 100 by 3 0 times. Okay. So 3 to the exponent 0 must actually just be 1. So 100 times 3 to the 0, in order for that to equal 100, that means the 3 to the 0 has to be 1. We can also see this if we graph y equals 3 to the x. There is a y-intercept right here. So when x is 0, that means we have 3 to the 0, and notice it's at 1. Okay. I've also attached another video in the class notebook showing you how something raised to the exponent is equal to 1. There's only one exception, and that's with 0. 0 to the exponent 0 is not equal to 1, but any other number it does. All right, that's it for this lesson. Hope you guys found this helpful, and I will see you later.